Okay, moving on to section 4.2. We'll work a handful of problems here. The first one being number 12, where we want to use the reduction of order, which is, if you look back in your textbook, looking in this section, it's formula number 5 in the section. And we want to do that to find the second solution, that y2 of this. So we're looking here at problem number 12. So first, we want to identify our p of x, right, equal to 0. And so we have that our y2 is equal to x to the 1/2 ln of x. We're going to take the integral e to the negative the integral of 0 dx divided by x ln of x squared dx. Okay, so when we simplify this, we have our x to the 1/2 ln of x. We have -1 over ln of x. And simplify that a little bit further, we get negative x to the 1/2. Okay, so our second solution then would be y2 equals x, negative x to the 1/2. Okay, sticking in section 4.2. Now we're moving on to question number 18, and we want to use method of reduction of order to find the second solution of the homogeneous equation and a particular solution of the non-homogeneous equation. So first we can define y as u of x times 1, which is just u of x. So that will give us that y prime is equal to u prime, y double prime is equal to u double prime, and y double prime plus y prime is equal to u double prime plus u prime, which is equal to 1. Okay. Now, if we let w equal our u prime, then we can obtain our first order equation the same, right? So we could say w prime plus w is also equal to 1. And it has an integrating factor, our integrating factor of e raised to the integral of dx, which is e to the x, right? So if we take the derivative e to the x w, we're just going to simplify that out to e to the x. It gives us that e to the x w is equal to e to the x plus some constant, we'll call it c1. Therefore, we could say that w equals u prime, which is 1 plus c1 e to the negative x. We could also say that y equals u, so x minus c1 e to the negative x plus c2. So from the last equation there, we see that a second solution is going to be y2 equals e to the negative x. And we could see that our particular is just x. Okay, so for this next, I believe we have a couple of these that we're going to look through here. We'll do one in this section, but that are using, so for this first one here, we're going to look at, given this higher order differential equation, we want to come up with a general solution, okay? So for this first one, I'll lay it out a little more, and then we'll kind of not do this first piece in the future ones. But first, we could say that our, when we have our y prime, that is, we'll use this m to signify that. So let's say that is, we should say that is our my. Our y double prime, we could say, is m squared y, and our third derivative would be m to the third y, right? So when we write this down and we translate this, given the equation that we've been presented, we can rewrite that as we just have y triple prime, right? So that's just going to be m3y. Plus we have 3 of these, so that's m squared y minus 4 of the my, right? Minus 12y is equal to 0. Okay, we can factor a y out of each of those terms, so that's going to give us m cubed plus 3m squared minus 4m minus 12, all equal to 0. Essentially, if we divide both sides by y, we can eliminate the y, and we're left with just the m cubed plus 3m squared minus 4m minus 12. We can actually factor that by grouping. So if you think about that, we can, just as a quick refresher, if we factor by grouping, if we factor these two terms, we can factor an m squared out of both of those. That's going to leave me with an m plus 3. From our second set, if we factor out, we probably want to factor where we have an m plus 3, so that where it leaves us with an m plus 3, so that we could then factor by grouping one more time and get that. So to do that, if we take out a negative 4, that's going to leave me with m plus 3, right? And equal to 0 still. And now we can factor one more time, right? You can see I have an m plus 3 in both of these terms. So I have an m plus 3, and I also have what it leaves me with as well. I'm going to write that one first. Let's do m squared minus 4, and then we have the m plus 3. And the reason I wrote it first how I did is because I always like to have the squared term first. That's the only reason. There's no, if you were to write it the other way, it wouldn't matter. Okay, so that gives us this here. So that tells me that my m is equal to, so m squared minus 4 is equal to 0, or m plus 3 equals 0. So when I solve that, I end up with m squared equals 4. So m equals plus or minus 2, because remember, when you take the square root of anything, it is the positive and the negative, right? Because negative 2 squared is 4, positive 2 squared is also 4. And so we have m equals negative 3 for this side, okay? So that gives me, we can have, let's say, one of our m's is equal to negative 2, m2 is equal to positive 2, and m3 is equal to negative 3. So we could come up with our general solution as y equals c1 e to the negative 2x plus c2 e to the positive 2x plus c3 e to the negative 3. Okay, for this next problem, still in section 4.3, similar to the previous, we have our y prime is equal to my. Our y double prime is m to the second y. So when we simplify this, we end up with 4m squared y minus 4my minus 3y is equal to 0. factoring out a y out of all of the terms, we have 4m squared minus 4m minus 3 is equal to 0. Dividing both sides by that y gets us to just the things inside of the parentheses. We can factor that to 2m plus 1 times 2m minus 3. So that means that m is equal to negative 1/2 or 3/2. Okay, so we can say that m1 is equal to negative 1/2 and m2 is equal to 3/2. So that gives us a general solution of C1 e to the negative x over 2 plus C2 e to the 3/2 x. Okay, so but this one we were given a initial condition, and so for that we want to say we were given y0 equals 1, so 1 is equal to our C1 e to the negative 0 over 2 plus C2 e 3 times 0 over 2. And so that's going to simplify to 1 equals C1 plus C2. So that's going to give us our first general equation. We were also given that y prime of 0 equals 5. Okay, so we have to first, what is our y prime? Y prime is going to be negative 1/2 C1 e to the negative 1/2 x plus 3/2 C2 e to the 3/2 x. Okay, subbing in what we have, we know that y prime is 5 minus 1/2 C1, not CI, C1 e to the negative 0 over 2 plus 3/2 C2 e to the 3 times 0 over 2. And so that's going to give us that negative 1/2 C1 plus 3/2 C2 is equal to 5. All right, so now we can take, let's take this equation from our previous slide, copy that to the next page. And we want to simplify this. So we simplify this to 3C2 minus C1 is equal to 10. So we can take our other equation where we had C1 plus C2 is equal to 1. We will utilize that over here as well. So when we look at this formula, that really can be rewritten as C1 is equal to 1 minus C2. We could plug that into the previous equation and get that 3C2 minus 1 minus C2 is equal to 10. And simplifying that, we get 3C2 minus 1 plus C2 equals 10. So 4C2 equals 11. C2 equals 11 over 4. Now we can plug that back into our 1 equals C1 plus 11 fourths. And that will simplify to C1 is equal to negative 7 fourths. So our equation would be y equals negative 7 fourths e to the negative x over 2 plus 11 fourths e to the 3x over 2. The next problem that we're going to work out of section 4.3, we're looking for this one is a boundary value problem. So similar to before, we have our y prime equals my, y double prime equals m squared y. So we can translate that as to m squared y plus 4my is not my, sorry, 4 just y, because there's no prime on that one, equals 0. So factoring a y out of each of those, we get m squared plus 4 equals 0. So in this one, we can't factor by our simple means of factoring. So we have to use our quadratic formula. Remember, that is negative b plus or minus the square root of b squared minus 4ac divided by 2a. So as a refresher, in this equation, a is equal to 1, b equals 0, and c equals 4. So when we plug that in to our quadratic formula, we get negative 0 plus or minus the square root of 0 minus 4 times 1 times 4. I'm going to actually scoot this over. All of that divided by 2 times 1. Okay, so that simplifies to 0 plus or minus the square root of negative 16 divided by 2. So that is plus or minus the square root of 16 times the square root of negative 1. I broke that out because, as a refresher, remember, you can't take the square root of a negative number. However, the square root of negative 1 is an imaginary number, so we can simplify this a little further to give us plus or minus 4i divided by 2, which simplifies to plus or minus 2i. Okay, so then we can have that y is equal to our c1 cosine of 2x plus c2 of sine 2x. Okay, we were given some initial conditions here. Given that y of 0 is equal to 0, we could say 0 is equal to c1 cosine 2 times 0 plus c2 sine of 2 times 0. Okay, therefore c1 is equal to 0. Okay, and we can also, we were given that y of pi is also equal to 0. So we have 0 equals c1 cosine of 2 times pi plus c2 sine of 2 times pi. Okay, you can see that's the same because 0 and 2 pi are essentially the same spot, just one time more around the circle. So we have 0 equals, or we'll write it as c1 equals to 0. Therefore, we would say that y equals c2 sine of 2x. Okay, next problem is out of section 4.4. This one I'm going to use quite a few different colors to kind of help draw your eye to how we are breaking this out, but we're going to look at this and solve this given differential equation by undetermined coefficients. So first of all, we have a homogeneous equation, which is this portion right here. This is our homogeneous equation. Okay. So we can translate that as m squared minus 8m plus 20 equals 0, right? Using our quadratic formula again, like we did in the previous example, we will get that m is 4 plus or minus 2i. Okay. Our complementary solution then is going to be y sub c. That is c1 e to the 4x cosine of 2x plus c2 e to the 4x sine of 2x. Okay. So now when we want to look at breaking out our different pieces, if we want to look at our partial, so our y sub p, that is going to equal ax squared. We're going to just use a, b, c, d, e's. So we'll have ax squared plus bx plus c plus dx e to the x plus e to the x, okay? And our y prime is going to be 2, so we're just taking our y sub p prime. 2ax plus b, c goes away, plus dx e to the x plus e to the x. And then when we do our second derivative, that is 2a plus dx e to the x plus e to the x. Okay, so now we want to put all of this together. Let's just use some colors. And so for the first part, we are looking at, we have this y double prime. So our y double prime is this piece right here. So we have 2a plus dx e to the x plus e to the x. The next part we want to do is minus this 8y prime. Well, our y prime is this piece right here, but it's 8 times that, right? So we need to do 8 times that, actually negative 8 times that. Put that in. Okay, so when we do negative 8 times that, we end up with negative 16ax minus 8b minus 8dx e to the x minus 8e to the x. Okay, next we are looking at this plus 20. So we're looking at this whole, our y equation. And so this is multiplying it by 20. So we get plus 20 ax squared plus 20bx plus 20d, not 20d, 20c plus 20dx e to the x plus 20e times e to the x. And finally, we have all of that is equal to 100x squared minus 26x e to the x. All right, we do need to simplify that. We can simplify that a little bit. This simplifies to, we have 2a minus 16ax minus 8b plus 20ax squared plus 20bx plus 20c minus 6d to the x plus 13 dx to the x plus 13 to the ex is equal to 100x squared minus 26x to the x. I'm going to take this over to the next slide because we have a little bit of work to still do. Put this up at the top. So now we want to, by comparing coefficients in the equation, how can we look at this, right? And so when we're looking at the coefficient, like we're going to say we have no x's here, here, or here, right? So that's 2a minus 8b plus 20c is equal to, on this side of the equation, we don't have any that are just strictly constants. So there are 0 of them. Okay. Moving on to the next one, let's look at where we have just a singular x. And so we have that with negative 16x. We have it with 20bx, and we don't have any cx's. Okay, so that's negative 16ax plus 20bx is equal, well, so we would just say without the x's. So we would just say negative 16a plus 20b is equal to 0 as well, right? We don't have any singular x's. This x here has the ex with it, so that will be addressed later. Okay. Let's keep going. We have our next one. Let's look at the x squared. So we have an x squared here, and an x squared here. So we have 20a is equal to 100. Okay, because remember, we're just comparing coefficients, not the x and the e to the x. Okay. Next one, let's look at, we have d, negative 6d e to the x and 13e e to the x. So that's plus 13e. And do we have any over here? No, we don't, not on the right-hand side. So that is equal to 0. Okay. Now let's look at where we have x e to the x as part of our coefficient. And so that is 13d is equal to negative 26. Okay. So now, based on these, we can actually, these equations, we can actually solve what is A, what is B, what is C, etc. So let's start with the easiest one. This one right here, we can solve and get that A is equal to 5, right? 100 divided by 20, A is equal to 5. We can then take that A and plug it in up here. If we do negative 16, 5 times 5, and then shift that all around, we can actually get that B is equal to 4 by plugging that A into that equation. We can now take and plug A and B into this first equation up here. So 2 times 5 minus 8 times 4 plus 20c equals 0. When we solve that out, we can get that C is equal to 11 over 10. Now we can also solve D, right? Negative 26 divided by 13 gives me a negative 2. Let me write that D is equal to negative 2. And plugging that up into the previous one, we can solve that E is equal to negative 12 over 13. Okay, so our particular is going to be 5x squared plus 4x plus 11 over 10 minus 12 over 13x to the ex minus 2x e to the x minus 12 over 13 e to the x. So to get our general solution, the general solution is just your complementary function plus your particular solution. So we'll come back over to this page to grab our complementary equation. Right, so our general solution is our complementary function plus our particular. We'll just put that plus here, and we'll make this also black font. Okay. Okay, another example similar to this where we're using our undetermined coefficients. So for this one, we end up with our m squared minus 4 equals 0. Therefore, our m is equal to plus or minus 2. So we can say that m1 equals 2 and m2 equals negative 2. So our complementary equation, C1e to the m1x plus C2 e to the m2x would give us C1 e to the 2x plus C2 e to the negative 2x. Okay, so for our particular, that's y sub p, that's going to be ax squared plus bx plus c times our cosine of 2x plus dx squared plus ex plus f sine 2x. Okay, so breaking this apart, we have negative 8a is equal to 0, negative 8b plus 8d equals 0. We have 2a minus 8c plus 4e equals 0. Negative 8d equals 1. Negative 8a minus 8e equals 0. And negative 4b plus 2d minus 8f equals negative 3. Okay, so simplifying this, we can get, so for the first one here, we get a equals 0. We can then use, well, this one here also is pretty easy. D is equal to negative 1/8. Let's now that we have D, we could plug that into this up here. We would get negative 8b plus 8 times negative 1/8. So that will give me that b is equal to negative 1/8. We have a, so we could plug that in down here. So we would have negative 8 times 0 minus 8 times e equals 0. So that means e also has to equal 0. Let's look at 2a, since we have a and e, we could plug that in here and figure out c. So 2 times 0 is 0 minus 8c plus 4 times 0. So c also has to equal 0. And then in the last one, we can do negative 4 times negative 1/8 plus 2 times negative 1/8 minus 8f is equal to 3. So f is equal to 13/32. So our yp is going to equal negative 1/8x cosine 2x plus negative 1/8x squared plus 13/32 sine 2x. Okay, so our general then is y equals a complementary plus a particular. Okay. So for this next problem, we are looking at an initial value problem. So we have m squared minus 1 is equal to 0. So our m is equal to 1 or negative 1. So our complementary would be C1 e to the x plus C2 e to the negative x. Just as a reminder, we have cosine h of x equals e to the x plus e to the negative x divided by 2. And so when we want to look at our particular, that's going to be a cosine hx plus b sine h of x. Our derivative, first derivative of that is going to be a sine h of x plus b cosine h of x. And our second derivative is going to be a cosine hx plus b sine h of x. Okay, so we want to sub into our differential equation. So this is going to be subbing that into our differential equation. Let's do a little bit of coloring. So we have here is our double prime. So that's this. So we end up with a cosine hx plus b sine hx. And subbing in for just our y, that is this up here. And so we're minusing a cosine hx plus b sine hx. Okay, and so all of that is equal to cosine h. So this holds for all of the values of x if a is equal to 0 and b is equal to 1/2. So we can say that our yp is equal to 1/2 sine h of x. So our general solution then, remember, that's our complementary plus our particular is going to be it's going to be our complementary plus our particular. So now we were given, though, that y of 0 is equal to 2. So that is y of 0 is equal to c1 plus c2 equals to 2. Y prime of x, so if I just do y prime of x, right, to get the derivative, is c1 e to the x minus c2 e to the negative x plus 1/2 cosine h of x. And so when I sub in our second condition that our y prime is of 0 is equal to 12, we're getting that c1 minus c2 equals 12. So we have here then that c1 equals 7 and c2 equals 5. So our equation is going to be 7e to the x minus 5e to the negative x plus 1/2 sine h x. Okay, for this next problem, it's a boundary value problem. And so we can say that we have our m squared plus 3 is equal to 0. So m equals plus or minus the square root of -3. So that is plus or minus the square root of 3i, because we'll bring that -1 out and make it an I. So y of h sub h, we're looking for our homogeneous here. So c1 cosine square root of 3x plus c2 sine square root of 3x. Okay, so a homogeneous differential equation is a type of ordinary differential equation where all of the terms involve the dependent variable and its derivative. and there are no non-zero constant terms or terms that are independent of that dependent variable. So our boundary conditions give the system where we have C1 plus square root of 3, C2 plus 2 equals 0. And so solving this gives us that C1 equals 2 times the negative square root of 3 plus sine square root of 3 divided by square root of 3 cosine square root of 3 minus sine square root of 3. For our C2, that's going to give me 2 times 1 minus the cosine of square root of 3 divided by square root of 3 cosine square root of 3 minus sine square root of 3. Okay. And so when we put all of this together, we get that our y equation is going to be all of this, plus we're going to add on out here our cosine square root of 3x plus all of this and we need to also add out on here our sine square root of 3x. And the last thing we need to make a little bit more room for is to add the plus 2x out here. Okay, so next we are into chapter 4.6. And in this section, we have our m squared plus 1 equals 0. So m equals plus or minus I. And so here we're looking, instead of x, we have theta. So our y theta is equal to C1 cosine of theta plus C2 sine of theta. Okay. And just as a refresher, we have P y double prime plus QY equals R, and our R is equal to secant theta tangent theta for this problem. Okay. We can compare with y equals C1U plus C2V, where U is cosine of theta and V is sine of theta, so that we don't have to keep writing sine, cosine, and make it a lot longer. So our C1 is equal to integral negative VR over W du, and our C2 is the integral of UR over W du. Okay, so we want to compute our Wronskian matrix here. So that is our W is, we have U, V, U prime, V prime. So that is cosine theta and sine of theta, right? And so then the derivative is negative sine theta and cosine theta. Okay. So that simplifies to give us that cosine squared theta plus sine squared theta, which that is a Pythagorean identity, so it is equal to 1. Okay, we need to solve for our C1. That is, we do the integral of negative sine theta secant theta tangent theta divided by 1 d theta. Okay. So this is, we could look at this as the integral of negative sine theta. Our secant is 1 over the cosine of theta, and then we have tangent theta. d theta. Okay, so that can simplify to negative tangent squared of theta. And so that is plus or minus, using another Pythagorean identity, we could say that secant squared theta minus 1. And thus, this is negative tangent theta plus theta. Okay. Now let's look at C2. When we're looking at C2, that is our integral of cosine theta, secant theta, tangent theta, all divided by 1, d theta. Simplifying, we get cosine theta, 1 over cosine theta, tangent theta, d theta. Okay, so we're looking at the integral of tangent of theta because the cosine and the 1 over cosine cancel out with each other. And so this gives me negative log of cosine theta. So when we look at our particular equation, that is going to be theta minus tangent of theta times cosine theta plus negative log cosine of theta times the sine of theta. Simplifying this, we get let's do the theta first. Theta cosine theta minus sine of theta, right? Tangent times cosine is going to give us a sine of theta minus sine theta log cosine theta. Okay, so our general solution is going to be C1 cosine theta plus C2 sine of theta that's our complementary plus our particular. Okay. Next problem, also out of chapter 4.6. So for this one, we have m squared plus 3m plus 2 equals 0. This is m plus 1, m plus 2 equals 0. So our complementary is going to be C1 e to the negative x plus C2 e to the negative 2x. Our matrix is e to the negative x, e to the negative 2x. And the derivatives then are negative e to the negative x and negative 2e to the negative 2x. That will give me a negative e to the negative 3x. Okay. Our f of x is just the sine of e to the x. That's our function. So if I want to look at u1 derivative, that's going to give me e to the negative 2x sine e to the x divided by e to the negative 3x. Okay, simplify to e to the x sine e to the x. Our u2 is equal to e to the negative x sine e to the x divided by e to the negative 3x. And that one simplifies negative e to the negative 2x. This is negative. Sorry. Negative e to the 2x sine e to the x. So our u1 is equal to negative cosine e to the x. Our u2 is equal to e to the x cosine x minus sine e to the x. So our our y equation is going to be our complementary plus plus our negative e to the negative x cosine of x plus e to the negative x cosine of x minus e to the negative 2x sine e to the x. And a negative and a positive cancel out with those. And so it leaves us with c1 e to the negative x plus c2 e to the negative 2x minus e to the negative 2x sine e to the x. Okay, this next problem, also out of chapter 4, section 6, we are looking to solve this differential equation by variation of parameters. So we have 4m squared minus 4m plus 1 equal to 0. So we end up with 2m minus 1 squared equals to 0. So our complementary is going to be c1 e x over 2 plus c2 x e to the x over 2. Doing our matrix, we end up with e to the x over 2. And here we have x e to the x over 2. Taking the derivative of each of those, we end up with 1/2 e to the x over 2 and 1/2 x e to the x over 2 plus e x over 2. That simplifies to e to the x. Our function is this e to the x over 2 times the square root of 1 minus x squared. Okay, so f of x equals e to the x over 2 square root of 1 minus x squared. So our u1 prime is going to be negative x e to the x over 2 e to the x over 2 times the square root of 1 minus x squared, all of that divided by 4 e to the x. That simplifies to negative 1/4 x square root of 1 minus x squared. Our u2 prime is e to the x over 2 e to the x over 2 times square root of 1 minus x squared divided by 4 e to the x. That simplifies to 1/4 square root of 1 minus x squared. So by using substitution, letting v equal 1 minus x squared and x equal to the sine of theta, that's a trig substitution. We get u1 equals 1 over 12 times 1 minus x squared to the 3/2, and that u2 is equal to x over 8 times square root of 1 minus x squared plus 1/8 sine inverse of x. And so it gives us our general equation, taking our complementary. So our y equation is our complementary plus our u1 and u2. For our general equation. Let me see if I can make this one a little bit bigger. Okay. This is the last problem out of this section that I'm going to work. This is problem number 20. So same thing, we're looking at solving the differential equation by variation of parameters, but we're given some initial starting conditions. And so this is problem number 20. So we have 2m squared plus m minus 1 equals 0. So we have 2m minus 1, m plus 1 equal to 0. So our complementary is going to be C1 e x over 2 plus C2 e to the negative x. Our matrix is e to the x over 2 and e to the negative x. So that gives us 1/2 e to the x over 2 and negative e to the negative x. Simplifies to negative 3/2 e to the negative x over 2. Our function is f of x is equal to x plus 1. Okay, so our u1 prime equals 1/3 e to the negative x over 2 x plus 1. Our u2 prime is negative 1/3 e to the x plus 1. We can also get that our u1 is negative e to the negative x over 2 2/3 x minus 2, and the u2 would then be negative 1/3 x e to the x. Okay, so our y equation then is going to be complementary minus x minus 2. Y prime on this is going to be 1/2 C1 e to the x over 2 minus C2 e to the negative x minus 1. Given our initial conditions, that implies C1 minus C2 minus 2 was equal to 1. So that is 1/2 C1 minus C2 is minus 1 equals 0. So we have C1 equals 8/3 and C2 equals 1/3. So y is equal to 8/3 e to the x over 2 plus 1/3 e to the negative x minus 2. The last type of problem that we're going to look at is out of the review section. So this one is really just asking you to verify that if y1 equals x e to the x and y2 equals e to the negative x, and their solutions are homogeneous linear equations, then show that y equals negative 5 e to the x plus 10 e to the x is also a solution. Okay, so to verify if y equals negative 5e to the negative x plus 10e to the x is a solution of this differential equation, we need to check if it satisfies the homogeneous linear differential equation. So we're given the two y1 and y2s, and we're given that they are solutions. And so remember, we can write this as y double prime minus p of x y prime plus q of x y equal to 0. Okay. And so if we're looking at our y1, that equals e to the x, right? And so from that, we can say then that when we're looking at y1 prime, referring up to look at this would give me then that e to the x plus our p e to the x, that's the p function, plus q function e to the x is equal to 0. Let's let that be our equation number 1. Our equation number 2, let's look at our y2. y2 is e to the negative x. So y2 prime is going to be e to the negative x plus p e to the negative x plus q e to the negative x equal to 0. Okay, our y3, let's say our y3 is equal to, we're looking at our negative 5e to the negative x plus 10e to the x. Okay, so y3 derivative then is going to be 5e to the negative x plus 10e to the x. Our y double prime of 3 is going to be negative 5e to the negative x plus 10e to the x. Okay, so when we put it into the equation like we did for 1 and 2, then we're going to get that we have negative 5e to the negative x plus 10e to the negative x plus p 5e to the negative x plus 10e to the x plus q negative 5e to the negative x plus 10e to the x. Okay. This is all going to, when you simplify it, we end up with 10 times, let's do 10e to the x plus 10p e to the x plus 10q e to the x plus negative 5e to the negative x plus 5p e to the negative x minus 5q e to the negative x. We can factor a 10 out of this first portion here. That's going to give me 10 times e to the x plus p e to the x plus q e to the x minus 5, factoring a 5 out of those, e to the negative x plus p e to the negative x. And this is actually going to be a negative because we're factoring a negative out. So that becomes negative. And then plus, we're taking the negative 5 out. So it leaves me with q e to the negative x. Okay. So from equations 1 and 2, we know, and the reason that we did that is if you look at this, and this is equal to 0, right? And this and this is also equal to 0. So we can, from equations 1 and 2, we can say that this is 10 times 0 minus 5 times 0. And so this is going to give us a 0. Thus, we would be able to say that y minus 5e to the negative x plus 10e to the x is a solution. So if you saw something like this on a quiz or an exam, it is not sufficient enough to just say yes, no, true, false. You have to show and be able to explain and articulate why it is or is not a solution.